Then we're having the Columbia Dodelson from Harvard. There was one Ringdown and finite property.
All right, well, thanks for the invitation and for the introduction. I'm going to tell you about this paper I just put out. Here's a quick outline. I'll talk about quasi-normal modes and how they encode black hole geometry. Then I'll explain how to compute them in perturbation theory, in boundary theory, and explain how the error of time emerges. And finally, I'll apply this method to SYK, and I'll derive the resulting spectrum, and I'll talk about it. Okay, so I'm interested in thermal correlation functions, and in particular, let me define CFT raised to the minus beta h O of t of 0. So I'm in some quantum system. I'm in finite temperature at inverse temperature beta, and this is some operator in the theory, and I'm considering the two-point function as a function of time. And I also want to assume that the entropy is infinite. So you can think of either a spin system at infinite volume, in which case the entropy is obviously infinite, or you can think of a system with infinitely many local degrees of freedom, like a large n theory. And in both cases, the entropy is infinite. And what do we expect? Well, we expect that this thermalizes. So at late times, CFT goes to 0. And the question is, how does it go to 0? Is it exponential? Is it power law? Is it exponential times the power law? Is it something crazy? Arguably, the simplest option is this. So this is one possibility, and it's pretty simple. It says that CFT is just a sum over an infinite number of exponentials. So these Dn are some complex numbers. Omega n are these complex frequencies. And in particular, since we wanted to go to 0 at late times, we want the imaginary part of omega n is less than 0. Okay? So this is one possibility. And I'll call this Ringdown. And the reason I call it Ringdown is because it looks qualitatively like what happens when two black holes merge. And the final signal at late times is dominated by the quasi-normal modes of the black hole merger, and that's called the Ringdown phase. And this looks similar to that.
So you want the imaginary part to be negative for all n?
Yeah, all that. I don't want any growing modes.
Couldn't they happen to cancel out or something?
Well, I think if they're discrete, then there's one with the highest. Any other questions? Okay, so of course, this connection between black holes and thermal correlators is made precise in ADS-CFT. So I want a Fourier transform. So I'll define C of omega is the integral over t e to the omega t. So t. And now you see what happens if we have this simple form. These omega n's just become poles of C of omega. And so now we can draw the picture of C of omega in the complex frequency plane. So here's the picture. So let's start. So let's work in n equals 4, and we start at very strong coupling, and now you can use holography to compute the correlation function, and we find the quasi-normal modes of the ADS5 black ring, and they look roughly like this. So in other words, we have a discrete set of frequencies at which there are poles of C of omega and which contribute to this sum. Okay?
Sorry, like maybe I came in late, but what guarantees that C of omega only has poles like no branch cut?
So at this point, I just made an ansatz. this is one possibility.
Yeah. But is there like an argument saying this is always true in the case of electricity?
No.
Okay.
So we're going to compute it. So that's one motivation for computing it, to show if this is true in a specific case. Yeah. Okay, so that's lambda equals infinity. And the other regime in which you can do computations is in free field theory. And here, in fact, it's not very long. So in this case, you find branch cuts. And they extend from minus k to plus k, where k is the spatial momentum of this operator. And so now we have cuts here, we have poles here, and the question in this talk is what happens here. Are there cuts, or are there poles, or are there cuts and poles? And I think we just don't know the answer. If you do, you can try to do a perturbative resummation around lambda equals 0, and various people have tried that in field theory, and you always find poles and cuts. Or you could try to use a naive holographic model where lambda equals infinity, and you only find poles. And so there's some tension that's happening, and we should get to the bottom of it. So let me also say that this is sometimes called the Christmas tree, because it looks like a tree ornament, but it doesn't. It looks like somebody forgot to put ornaments here, and we'll discuss that in this talk. So here at finite lambda, we have some kind of stringy black hole, because lambda in the bulk is alpha prime, and so alpha prime is finite. It's a very non-local black hole, and so the question we're asking is, how do stringy black holes behave when you probe them?
And your thing is strictly n equals infinity and change to lambda?
Always, yeah.
Okay.
So it's really the simplest thing. So I say it's a stringy black hole, but I don't really want to deal with metrics, because that sounds like a mess. So instead, I'm just going to look at this spectrum. So I forget about geometry and just look at this spectrum of resonances, and then hopefully that'll tell me something about the black hole geometry. So that's kind of the motivation. Any questions up till now? Okay.
Just the details.
Yeah.
But in defining C of T in general, you use, you don't put any time ordering or anything, you just put the Wilson 2-point function.
Yeah, so this one is white. Yeah.
Sorry,
Yeah.
why? So that's good.
Yeah, you could also do the retarded Green's function. That one only has poles in the lower half plane. The one I defined here has poles in the upper and lower half. Okay, so you start at lambda equals infinity, and in this situation, if you work above the Hawking-Page transition, all you have to do is to look at the classical wave equation on an ADS black hole background. So that's what ADS-CFT tells us. So we have some metric, which is I'm not going to specify what f of r is, and I'll just keep the discussion general. Okay, so that's the metric. And then we have some wave equation for a scalar field on this background. And here Z is the tortoise coordinate, just to find out this. Okay, and now to compute, say the retarded Green's function. So, say we want to compute G retarded. What you do is you look for a solution psi of Z, which is purely ingoing at the horizon, which is Z is infinity. So this is the purely ingoing wave at Z equals infinity. And then at the boundary, it has some generic behavior, which is non-normalizable plus normalizable. And the retarded Green's function as a function of frequency is defined as B of omega over A of omega. Okay. So you can see that something interesting happens when A equals 0. So this is a pole. So it's a pole of the retarded Green's function. But also you see that the non-normalizable piece near the ADS boundary, this is equals 0, the non-normalizable piece vanishes. And so we have an ingoing normalizable solution, and this is called a QNM, a quasi-normal mode. And yeah, so this A equals 0 condition can only happen when omega is in the lower half plane. Okay? So let's do an example. So our example is going to be an ADS 5 black ring. And now we have our potential. And if you plot it as a function of R, it looks like this. Okay? So you have your horizon, RH. You have R equals infinity, where it diverges. And you have R equals 0, which is the black hole singularity. This is the ADS boundary, this is the black hole singularity, and this is the black hole horizon. Okay? And as I have up there, we have this Christmas tree. Okay. So these can be computed numerically by solving this wave equation on a computer, or you can compute it out here asymptotically using the WKB approximation. So now there's two interesting limits of this function, obviously. You can go out here, or you can go down here. Okay. So the first one, omega to plus infinity, is natural, because this is the high energy limit of the correlator, and no analytic continuation in frequency is necessary. Omega to minus I infinity is strange. It's not something you would normally do, because normally you just have the function on the real axis. And so what does this mean? So actually this probes the black hole singularity. So I'll explain why that is. So suppose we look for a turning point in the WKB approximation. So a turning point in WKB is defined like this. When the potential is equal to omega squared. Omega being the frequency. Okay? So now, if we take omega goes to plus infinity, you see that the potential has to be large and positive. And so we're probing R equals plus infinity. So this is just probing the boundary. This says that high energies in the correlation function approach the boundary of ADS. This is the OPE, the operator product expansion limit of the correlator. But now you see that if omega is minus I infinity, then the potential has to be negative. And the only way to get a large negative potential is to go to R equals 0. And so this is probing the black hole singularity. Okay? So, to sum up, if you want to see the black hole singularity, you should analytically continue down into lower half-time.
Yeah, but this fact depends on like what metric you're considering, right? Like having omega going to minus I infinity correspond to singularity depends on the metric, right?
So here I was doing a specific example, which was the ADS5 black ring.
Yeah, like say for example you have say order horizon, is it obvious to say where this V of R going to negative infinity?
So it's, if you have an outer and inner horizon, it's still going to probe the black hole singularity. You're just going to have a more complicated structure. Asymptotics. Okay, so let's just, so the WKB approximation is equivalent to the geodesic approximation in the book. And so we can draw the geodesic that's being probed here. So this is the Penn.
Can I ask a follow-up question?
Yes.
You said if you have an outer and inner horizon, that's omega to minus I infinity is still gonna probe the singularity, but in that case the potential will become positive instead of horizon, right?
Yeah, that's right. So, yeah, so in the case you mentioned, the potential is like that.
Yeah.
So now what it does is you end up going to R equals 0 still, but you approach it in some complex direction. So So in a charged black hole, the quasi-normal modes, there's not just these. There's also purely imaginary ones. And now you have to take this asymptotic limit. So it's a more complicated, complex asymptotic limit. And this is the limit that probes the singularity inside. Thank you. Okay, so let's just explain which geodesic this is. So in WKB, every turning point corresponds to a geodesic. And the one, as you probe omega to minus I infinity, corresponds to this one. So it kind of bounces off the singularity. And this is what's being probed in this limit. And I'm just going to quote an answer, and maybe you can remember this for later. The magnitude of the correlator, sorry, I meant to say this. It behaves like e to the minus constant times the imaginary part of omega as omega goes to minus I infinity. So it exponentially decays. So the correlator down here exponentially decays, and there's some decay constants. So this is a concrete signature of the black hole singularity, and I'd like it if you kept that in mind. Any questions while I'm doing this?
Sorry, you with the WKB turning point,
Yeah.
you already made a connection between omega going to minus I infinity and R equals 0.
Yeah.
Now you're saying that this C, absolute value of C omega being like this is a signature of black hole singularity.
Yeah, it's just, that's what happens if you evaluate the correlator on that geodesic. That's the contribution of that geodesic. All right. Okay, maybe let me give you a second example. I'll just say this real quick. So, I mean, the whole point of this is to convince you that quasi-normal modes encode geometry. So let me tell you another example really quick. So, as you may know, black holes have a photon sphere. And the way to see this is to take a Schwarzschild black hole, but now it's finite volume. So not a black ring, but finite volume. And now the potential looks like this. So instead of being monotonic as a function of radius, it now has this unstable maximum, and this is called the photon sphere. You can show that the geometry of this photon sphere, up to a technicality that I'll say in a minute, is encoded in these quasi-normal modes by the following relation. So this is in the limit L goes to infinity, and L is the spin, and so you go to a very large spin, which is the icon limit. Omega is the velocity of null geodesics at the photon sphere, and gamma is the Lyapunov exponent. It measures the instability of the photon sphere. The technicality is this isn't actually right. I have to put an I there. So that's the technicality. But if you want to see signatures of the photon sphere in the boundary CFD, you should go to large imaginary spin, and you should look for this behavior. Okay, so those were a couple of examples.
If I remember well, the same kind of potential arises in worship black holes which are small, much smaller than the ES radius.
Yeah.
Is there some relationship with that?
So, well, in asymptotically flat black holes, for instance, this relation holds, but you don't have to go to large imaginary spin. In ADS, you have to go to large imaginary spin. And if you do that, you recover exactly the flat space limit of the spectrum. More questions? Okay, so let's go to the boundary. Okay, so now I'm going to tell you how to compute these quasi-normal modes on the boundary. I'm going to make a few very simplifying assumptions. The first assumption is that it's at infinite temperature. So in other words, we're computing trace O of t over 0, and we don't need to put e to the minus beta h. The second assumption is that we're just doing quantum mechanics, and so this is non-singular at t equals 0. So in quantum field theory, this would have a coincidence singularity, and we're not going to consider that. And finally, we want a single dimensional coupling, J, and it has units of energy. Okay? So this is CFT, and we can note that CFT is even because of this formula, and so we can make a Taylor expansion in CFT because it's non-singular at t equals 0, and this is called the moment expansion, which people at Berkeley famously discussed in great detail. Okay, and these mu2n's are called the moments. And so because of my assumption, there's only a single dimensional coupling, and so these mu2n's have to scale like j to the 2n. Okay? So what this tells me is this moment expansion, this Taylor series in time, is just the perturbative expansion of the correlator, because the nth moment is proportional to j to the n. And the important thing here is that this is convergent. So it's not asymptotic, it's actually convergent in a finite radius of convergence, where t is less than t star, which is proportional to 1 over j. Okay. So if we compute a lot of these moments, we can compute the correlation function extremely well for t less than 1 over j. We can't go beyond that at all.
What is J?
J is our coupling. We have a single dimensional coupling, J.
Oh, all of them are capital J.
Yes, everything is capital.
Oh, okay, good.
Okay, so suppose we were able to do this to compute these mu2m's. So we have a signal over a very short time, and we need to fit it to the sum of exponentials. Okay? So our fitting equation is C of t. And this is convergent for all times. So if we're able to fit this moment expansion to the sum of exponentials, we've now solved the problem of computing the correlation function for all times. So that's pretty cool, because it means you can use perturbation theory to study the late time behavior of the correlation function. You might have thought you couldn't do. And the reason you might have thought that is because these omega n's are proportional to j. And so it looks like you're doing some non-perturbative resummation of the correlator to go to late times. And that sounds hard, but in fact it's solved by this exponential fitting problem. So the only thing we have to do is to fit this function to a sum of exponentials.
Sorry, just to make sure I understand the logic, you want to get C of t out of that convergent sum and then assume analytically continue and then match.
So we have our short time signal. We want to fit it to some exponentials, and then if we're able to do that, we automatically get it for all times.
So that ansatz is general ansatz for all t.
Yes, and this is very well behaved at late times because each term exponentially decays, as opposed to this where each term grows.
Oh, sorry, yeah.
Any other questions about the logic?
Sorry, so you match them as small t.
Yeah.
Okay.
And then we go to very late times.
Using the exponential one to go to late.
Yeah, exactly. Yeah. So it's a non-perturbative method. So this actually looks like time evolution with some non-unitary operator because these omega n's are complex. So that's part of the strategy. We want to construct that non-unitary operator. So the way to do this fitting is to solve this equation on a grid. So the first thing that we do is we truncate this sum of exponentials to a finite number s exponentials. And we solve this equation for j equals 0 all the way to 2s minus 1. And so these are discrete times, equally spaced, and we have 2s equations we need to solve, and we have 2s unknowns, which are the dn's and the omega n's. So that's enough equations to solve for these. So just to draw a picture, we have our function, t, c of t. We know c of t very well up to t star, which is the radius of convergence. And then we want to fit it to exponentials on a grid with 2s points. So here s is going to be 1, 2, 3, 4, 5, 6. Well, let's put another one, and now it's 4. So the way to solve this this problem, as I said before, is to construct a modified operator whose eigenvalues are these omega m's. So I need to introduce some notation. So I'm going to have a Hilbert space of operators, and they have the following inner product. And so this defines the Hilbert space. And I'm going to define an operator U tilde by the following thoughts. This says that the jth power of U tilde acting on this operator overlap with O is equal to the correlation function at J times delta T. And if you compare this equation with that equation, you see immediately that U tilde has eigenvalues which are equal to e to the minus I omega n delta T. Okay?
So when we take S modes in exponential, are you thinking that this is a S slowest decay?
Yeah.
Yes.
Effectively, that's what happens. Yeah.
You're saying that's enough to get the approximation for the S. And then to match this to the first portion of the alpha W thing, do you assume that you know n to n or order?
M to n?
Or you moment?
Oh, yeah. So we truncate the moment expansion, so we compute the first 200 moments. And that's going to give a very good approximation over this range.
So if it's bigger than 2s or whatever, it's okay. And then
Exactly.
you keep increasing s.
Exactly. So you want to take mu to or the number of moments to infinity first, and then you want to take s to infinity. Exactly what you're saying. Okay? So, yeah, so we have this eigenvalue equation, and you can solve for the eigenvectors using this nice ansatz. So you just sum over time-evolved states. So this is the ansatz with some coefficient functions p and j. Plug in this ansatz here, and you use this relation, and you find a generalized eigenvalue equation, which takes the following form. And these matrices MI, MN, IJ is defined just to be the correlation function. So the matrix elements of this matrix are the correlation function evaluated on discrete time points. So all you have to do is plug this into a computer, and it will tell you the answers for these omega n's. And that's what you want. And now we take s goes to infinity. So s is our truncation number in the number of eigenvalues. Now we made an assumption. We're not guaranteed this form. There's no magic. But if our assumption was correct, and we have a discrete spectrum, then this will give the right answer. If our assumption was not correct and there are branch cuts, it's going to give accumulation points in the spectrum, and that's the signature that our assumption fit. So we have to check case by case. I want to mention that in the bulk, U tilde, this modified time evolution operator, U tilde, corresponds to an I epsilon prescription at the horizon. So this is this double chrome story of Molisana and Chen. Saab chambers. Okay? You clear how to do this? Yeah, I guess I'll also say that this strategy is often used in classical chaotic systems. So in that context, you can also define these resonances as eigenvalues of some coarse-grained time evolution operator utility, and it's a very similar story there. So, that's the context in which this is most usually applied, not usually to quantum systems.
Can you just say again, what's the definition of n sub n?
Yeah, sorry, it's impossible to read, but it's the correlation function evaluated at I plus j plus n times delta t.
That's the definition?
Yeah, that's the definition. And so this is an equation that if you know C at every point on the grid, you can just make these matrices.
And what's the point for the equation above?
So these are the matrices that you plug in and then you solve for the omega n. This is an eigenvalue equation. It's a generalized eigenvalue equation. If this m0 was the identity, you can see that this is just an eigenvalue equation, right? For m1. Okay, so now let's apply this method. And we need a model where we can compute these new UNs very well. It doesn't particularly matter what model we choose, as long as we can pick as long as we can compute the UNs very well. And the best model I know is this SYK model, which is defined like this. Because we're in 2024, I call it P and not Q. So we have P fermions that are, sorry. You have N fermions and P pairwise interactions. And we take N goes to infinity. And in this model, you should average over the coupling constants. And this defines the coupling J. So you recall in my assumptions, I had this one-dimensional coupling J, and that's it. This model satisfies all the assumptions I have. It's quantum mechanics. Non-singular at t equals 0, we can compute it at infinite temperature, and it has a single dimensional coupling J. So it's a pretty good model. So the reason this model is real simple is because we have these Schmier-Dyson equations at infinite n, and just to draw them out, these are equations for the exact propagator, the exact 2-point function, and schematically they look like this. You have the free plus this kind of behavior plus things like this, and you can take this picture and write it as a formula and put it on your computer. And when you do that, it will tell you the answer. There's an algorithm in polynomial time to tell you these mu2n's. And so you can just let it run on your computer for as long as you want. And spend, I guess, a couple months doing that. And you find 2,000 moments. And so this is a precision of 10 to the minus 1200. So we know that the signal on a very short time scale, it's a pretty good precision. And we need all this precision. The reason we need it is because we're trying to compute frequencies that are deep in the complex plane. These just are killed right away. So you better know the function really well. If you only want the first, the lowest minimum, it's much easier. You only need order 10, 20 moments. But we're interested in more solid questions. Okay, and here's the answer. So, first thing you find is our Christmas tree. I found, I think, around 40 converged poles. So we have our Christmas tree, but then we have poles inside, and try to give you a basic idea of what they look like. But they're more random than the ones on the outside. So maybe they're more random. So we have a filled-in Christmas tree, and the ones up here converge much quicker. And up to here, we have 4 digits of precision, and down here it's a little bit less precise. Okay. So I want to comment on a few of the features. The first feature is that it's meromorphic. So this is our best case scenario. There's no cuts, and there's no accumulation points of eigenvalues. Everything, even though there's a lot of poles, they seem pretty well separated. And nothing accumulates. Second property is we have a Christmas tree. And the third property, if you compute the residues of these poles, which are the dn's, these exponentially decay. So I wanted you to remember this was the signature of the black hole singularity, and here it's still true in this regime, which is very non-holographic. I want to emphasize this is way more holographic than it has any right to be. It looks a lot. Certain aspects of it, these 3 aspects, look a lot like an ADS black hole, even though we are very far away from any holographic regime. So that's the surprise. Any questions about any of this?
In what sense is finite lambda?
Because the Lyapunov exponent is not 0, but it's not maximum.
What is the transition to cuts happening from lambda to 0?
So in this model, there's no. At the end, I'll tell you a related model in which there are cuts, but in this model, there's no actual limit in which you get cuts.
Oh, all the way to lambda to 0.
That's right.
What is actually the definition of Christmas tree when they're random like this? Is it they're bounded by some rays? Or?
Yeah. I want to say that the edge of the spectrum is linear.
Okay.
And is P equals to 4 important?
Okay, so let me talk about that now. Any other questions about P equals 4? Okay, so this is a fun result. So this is the result of the talk. And now we can do a little bit more. So one thing you can do is go to infinite P. And in this limit, there's no Christmas tree. The poles are all imaginary.
So you said this result is for equal 4?
Yeah. But it's any finite P. So this is P equals infinity. And the interesting thing about this People's infinity limit is that there's secretly some ADS2 holographic dual.
What do you mean by infinity? Like scaling with n?
N is strictly infinite, and then I take P very large.
So this is not like double scale, that's what
It's just single scale. Or is it triple scale?
Right. So you take so you take n to infinity first,
Yeah.
and then p to the infinity.
Yeah, so what Lynn and Stanford showed was that there's some secret ADS2 dual with an ADS or ADS that depends on beta times J. So this model is secretly holographic, even though it doesn't look like it. And in other words, you have a redshift factor, which is r squared minus 1. And you don't need any fancy technology to verify this. You can compute in this metric the quasi-normal modes, and you'll find this structure. The fact that it's not a Christmas tree is just the fact that in ADS2 there's no black hole singularity. Now we see that as we transition from P equals infinity to P equals 4, something must happen. And in particular, this has to open up into this Christmas tree. And so you can do a really crude toy model, which is take your r squared minus 1 and then add something that diverges that order. And it actually doesn't really matter what you add. It always opens up. So you can compute the numerical PNMs in this metric. You always find it opens up. So this is kind of a crude model for the transition from P equals infinity to P equals 4. Okay, so
How do those extra terms depend on p?
well, you would have to fit them, but the only thing I know is qualitatively it opens up as you turn on these extra terms. So these extra terms should be 0 at p equals infinity. They should be small at large p.
So what's the intuition that finite p gives us singularity?
Well, I guess at infinite p you have ADS2, and then finite p is some perturbation away from that. And
But what is p in the bulk? Is it?
oh, I couldn't tell you that.
It's not obvious. I mean, that's just, as you said, a crude toy model. It's not clear that there would ever be a match between those coefficients and p.
And in fact, this toy model doesn't really work. I'm not going to get into it. You can read my paper if you're interested in those technicalities.
So DNs do not exponentially decay the ADS2 tables.
Exactly. Yeah. They polynomially grow or decay. Yeah. Okay, so before I conclude, I want to come back to this picture. So what this calculation did was it told me basically have it up to here, so that we don't really know what goes on down there. And maybe if we want to understand the black hole singularity, we should figure out what the spectrum looks like down there. And I guess it's random matrix theory. So why is this a good guess? Why is this a plausible guess? If you take an open system, you can consider random open systems. And thermal systems are kind of like open systems. If you consider random open systems, you have a spectrum which is very universal on the edge, like this edge, and then in the bulk, it transitions into random matrix theory. So you imagine that the same thing might happen here. So that's my guess, and one needs to check it. Okay, so I guess I'll give some deeper directions, but are there any questions before that? Perfect timing. Future directions. That's great. So here's some future directions. one question is, how general is meromorphic of the 2-point function? So I've given you one example where it's meromorphic. How universal is this structure? Let me say one thing. This can be actually proved in classical systems, assuming that the system is highly chaotic in a sense, which I won't explain right now. There are certain assumptions under which you can prove meromorphism. And one wants to understand what the quantum analog of those are. And if these assumptions don't hold, then there can be branch cuts. And so here's an example of an SYK model that I find has cuts. So if you take so our standard P=4 model, and then you mass deform it. At low energies, this flows to an integral model. So it's not really that chaotic anymore at low energies. And numerically, I find cuts in this model. So I guess the future question is, what does that mean? Can we characterize all systems that have branch cuts in the spectral density?
This theorem says that even if the whole number is not infinity, you have alpha parameter. As long as it is infinity, it's still
This theorem in classical. So in classical systems, there's no n or lambda. It's literally just like a particle bouncing around like a pinball system. So it's classical chaos. So that's the only system in which that's
okay. So it's not particle class.
No. But I mean, in bulk, it's true. In bulk gravity, you can prove meromorphic. But yeah.
Any attempts to do that using string correction or something? No.
I think the problem is, as soon as you have just a finite number of string corrections, you haven't really changed. You haven't really done anything. You would need to resum all the string corrections, and it's hard to. I don't think we even know the first correction, the first coefficients of it. So it's hard to know how to do it. But yeah, I agree that would be interesting. Here's another question. So there are these higher dimensional SYK models. Sean has some, and there's this modest Morgan Stanford Witten model. And in higher dimensions, now we can start asking the questions like, is there a photon sphere? So I briefly told you how to see a photon sphere in the spectrum of quasi-normal modes. And if we can do it here, then maybe we can try to look for a photon sphere in a CFT where we can do the calculation. And the most interesting thing is more realistic systems. So, for example, what is the lowest quasi-normal mode in the 3D Ising model? We just don't know. I mean, it's not known experimentally, it's not known numerically. You should compute it.
Why is it not known numerically?
It's real time, so how to do it. So one idea, and actually Severe Sasha told me that they're going to measure this thing, so we should compute it first. So one possible way to do this would be to consider the system on a lattice and go to the quantum critical point. On a lattice, you could try to compute the moments, and then you could try to do this. So that's something to try. Okay, thank you.
Can you explain again why this finite P is analogous to finite lambda?
Yeah, it's more just that infinite P is analogous to infinite lambda. So at infinite p, you can compute. I guess I don't know why. There's an SL2R that emerges in the p equals infinity limit for a reason that's unknown to me. But when you go away from p equals infinity, that SL2R is broken, and so it's more like a string.
So in your introduction, you were saying you wanted to stick to strictly infinite n, but isn't p more analogous? I'm a bit confused about how you're relating this to your introduction.
You're asking is p more analogous to n?
Yeah. Or just it's not straightforward to me the way you're relating.
I sometimes. Yeah, I see. Yeah, I mean, just in the sense that a more natural thing you could do is to start at low temperatures, and at low temperatures we have a real holographic limit, because then it's dual to JT gravity. And then you could perturb away from low temperatures, and then it's like having finite lambda effects, because you have higher derivative couplings in the JT gravity bulk. This is kind of like that.
Sorry, I thought you want to say that is the thing on the left is more like that.
This is like finite lambda.
Yeah.
Yeah, finite lambda. P is like lambda. N is already infinity, right? N is already infinity. And G is 0, of course. G squared n to be finite.
I thought lambda is like beta j.
That's what P. And then you also send lambda infinity. It goes to the classical geometry. That's what.
But yes, that's not right?
I don't know what.
I would forget about lambda and just think about the Lyapunov exponent.
But the tricky thing is that the Lyapunov exponent barely depends on p.
Barely depends on.
Yeah, it depends on p very weakly. So I think when you goes from p equals to 4 to p to infinity, the correction to the Lyapunov exponent changes by less than 1 per person.
Oh, sorry.
So
yeah.
But something drastic in the quasi-normal spectrum happens.
Yeah, it's this weird fake disk story. There's this emergent SL2R. I don't understand it. It's just, I don't know the physics, but it is a fact that at p equals infinity, you can compute it in ADS2 and you get the right answer. So I guess that's all I want to say.
Yeah, I have a very basic question about the King geodesics. So those can, if you try to compute two-point function, like two-sided two-point function in a black hole space-time, is there like a specific time at which they kick in and they become the nominal contribution, say in the geodesic approximation?
You mean in real space?
Yeah.
In real space, I don't know if they're ever the dominant contributor. There's some words in the original Ficassi paper which say you can analytically continue on the second sheet. I don't know how to do that, which is why I prefer to stick to frequency space. And then it's pretty clear how to do it. You just take these asymptotic limits in frequency. But yeah, to answer, I think it's much more subtle in position space.